Hello everyone, it's October the 9th. Let's do yesterday's challenge. So the goal is definitely we finish this, and I have another kind of idea for the calendar one, so I'm going to try that other one as well. If we still have time, we might do another thing, but we'll see. But this is an easy one, so I'd expect to finish this fast. Given the root of a binary tree and target number k, return true if there exists two elements in the BST such that their sum is equal to the given target. Oh, it's a binary search tree, right? If it's a binary search tree, so you give a root and you give a target. There exists two elements that their sum is equal to. Okay, so what we can do is, number of nodes, 1 to 10 to the 4th, guaranteed a binary search tree. One way we can do is just turn the whole binary tree into a set. We can always do that. We turn it into a set, and so it's O(n). But I'm pretty sure we can do it O log n. All right, let's say 5. We need to find 4, so we go to this side, right? And how do we try to find a 3 and 6? I guess it's 3, so we need a 6, and then we go to the top to find a 6. So maybe what we can do, we iterate through. But if we iterate through everything, then what's the point? Right? What's the point? What we can do is we go down the left path, right? We'll get all the smallest. But that's still not, it's not answering the question. The question is, if we have this situation, like a 2 and a 7, how do you find them? Right? You go down, and then you get a 2. Or we do this. We just go all the way down, because we can traverse it in a sorted manner, right? So we go down to 2, right, and say, okay, we need to find 7. So we go back to the front again, and we're trying to see if we have 7. And that's a binary search, right? That's a binary search. And then if we can't, we go for the next one, is 3. And now we're trying to find 6. We go from the start to find 6. And then 4, we go from the start from 5. And once we reach the top, which means we have traversed the smaller half depending on this, and yeah, it might be on the right side, so you have to keep going for everyone. But that's O(n) log n, right? That's O(n) log n. We could have done this in O(n) by using space. It doesn't say space is, so maybe we can try both. I'm not sure what the question is trying to ask, but we can basically try both. I will try the method that surely works. You might say it's a stupid method, but honestly, it's not. Okay, this is not a stupid method. I think it's a highly valid method. We just have a nums. We set it to a set, right? And then we say def dfs node. We don't return anything. Say if node nums.add node. Oh, is it repeating or not repeating? A valid binary search tree. I think it's not repeating if it's binary search tree. Yeah, I think it's not repeating. Let me just go node.left, node.right. Right? And then once we're done, we just say For n in nums, if k minus n is in nums and k minus n is not equal to n, then return true. Otherwise, return false. That will be my kind of first idea. And we can try this. What? How? Man, these things are getting wild. Oh, no dot vowel. Yo. Hold on. This has to be this. I don't know what happened. Has to be no dot vowel, and this has to be this. Wait. What was wrong? Gotta be kidding me. Left, right, we added a value. Oh, for sure. Because I forgot to call it. Like all the problems I have. Always forgot to call it. Ah, I think that's right because it didn't really say anything about. We'll see. Yep. So this kind of, no, it's not the ideal way that we want to do it, but it works, right? Call this O(n), but also O(n) additional space, right? Additional space. I could have sorted it, so I could have sorted it, but yeah, kind of lazy. But of course, this is not what this problem is hinting at. Pretty sure. So the problem is hinting at is binary search, right? It's binary search. So this is a cop-out solution using a set instead of binary search. All right, so let's now try our hands at binary search. So my idea is we will always find. Yeah, I'll check this, right? And then if it doesn't work, I'll check. Let's go left first, and then I'll go left, right? And then I go right. Yeah, if something, yeah, things shall work. For DFS node, I'm going to return a Boolean value and current target. Say if node, if not node, false. Otherwise, if node.val equal to current target, true. Right? Otherwise, I simply no, hold on. That's DFS. We all have binary search and DFS. We have two things. Then why do two recursion? We can just BFS it, Like, it doesn't really matter, right? We can just BFS it, so we can say, all right, let's do this binary search. Yeah. If this, yeah, this is binary search, right? Now we say if current target is smaller than no.val, then return binary search no.left current target, and I also return binary search no.right current target. Yeah, this is a binary search. And then I'm just going to traverse the whole thing using as simple as a queue. Right, while queue temp equals this. Right, and I say for node in queue, and then we say if binary search node dot node and hold up. I take this and I need to search from here for the target. Yes, so this is the root. This should be the root. Right? And because it's a binary search tree, so it shouldn't be repeating. So we say root and n minus node, not k, minus node.val. If it's true, and k, maybe we can even do better. Yep, let's do better. Let's do optional tree node. Right? So this will just return none. If this will return node. Right? So then we can get a, let's say, potential node equals and such. So if potential node is not node and, no, not and, if it's not node, if potential node is not node and potential node, if potential node and potential is not node, then we'll return true. That means we'll find it. Right, find something. Otherwise, we don't find it, then we just say temp dot append, no, if node dot left, temp dot append node dot left, if node dot right, and then q equals temp. Right? Yeah, we return the node. The benefit is we can check. Right? Even if we have duplicates, it's okay because it cannot be the same. And then when I break out, I'll return false. Let's try. See how this one goes. Did you call it? Yes, I think I called it. Binary search, I call it. Let's try. Root. Okay, seems right. You want to try this? Yeah, why not? Let's see. That's gonna run a little bit slower. So I say this is ON. log in using binary search naively. So to get it faster, maybe we can do binary search smart. How would you smart doing binary search like this? Maybe what we can do is how do you know it's half? Well, you do know because the target, k, right? So if I'm on the left side, I need to find something bigger. And until I find something, so maybe what we can do, let's go solution 3. I think there is one more solution in there. Keep the binary search, right? We keep the binary search. This one is good. What we want to change is instead of doing this way, I will do DFS node. This is just traversal. And this one doesn't return anything. Well, actually, it can return Boolean value, right? So we just say if not DFS, not node, turn false. Otherwise, we'll left root right, right? So we always call node.left. I can check the value. We'll just say if k minus node.val, right? This one should be larger. If this is smaller, then node.val. Then we just return false, which means we have hit everything on the other side. So we go small, right? For small one, I want to find a big one, right? From the smallest, I need to find a big one. But if it happens that the two got swapped, so the current one is a big one, that just means we cannot do anything, right? Otherwise, we always go left, go to the bottom left, right? And now we handle node itself. Then we just say binary search, right? Node. I take this node. Oh, then there's a node root, and we say k minus node.val. That's our target. So we binary search it. So we say potential node equals this, and if potential node and potential node is not node, then we're going to return true, right? And then we say DFS node.right. And of course, we say if this is true, then we return true. Otherwise, we do this. And we say if this is, oh, then we just return this. So that's the DFS. So we just do DFS root. Okay, let's try this one. Oh, solution 3 has no 3. First one is not right. I stopped going. So I cannot do this. Oh yeah, I need to keep going. And then whenever I hit, because now I hit, it's following the thing. Then I can do it here, right? Let's try this. Okay. How does this one go? It's about the same. Alright, I got 3 methods in. This is a binary search as well, and O1 space. Also call it O1 login. Alright, so what are the good ideas? Let's see. Yeah, I'm pretty sure the number of test cases is more in this one. So, oh, that was a good one. 422. Now it's the same. Damn, it didn't do as well. So what was this smart? What's this? A BST iterator. Push left, push right. Oh, I see what it's trying to do. It's the same thing. A 2 iterator, one on the front, the other at the back. And then if the sum is larger, then we move the left, or move the right. Oh, very nice. Very, very nice. I see. Ha, this is what the interviewer trying to get. I think this is the solution I passed. What's this one I use? Oh, that's the set idea. Always fast. No, I think they changed the test case a little bit. But that's a valid idea. You can try. Solution 4. BST iterator. Treat the binary tree, treat a BST, right, as a sorted array, and we go from both ends toward the middle. How would you consider the runtime? But how do you back up? Hold on. How do you back up? Oh, you have to do your own stack. I see. It is a standard twosome problem where if sum of the 2 iterators is larger than k, we move the right, left, otherwise the left, right. We need to keep 2 stacks to save the info, to manually traverse manually create BST iterators. def it's all the way down left. Down left. Right? Say if node, optional. A while node equals node.next, node.left. So what do we return? So while node.left, right? Return node. While node, all right. Oh, hold on. We need to save these left stack because I need to unwind the stack. L stack, R stack, right? While node dot left, we need to L stack dot append node equals this, right? Return node. Same thing. R stack node, right? Return node. Okay. Then next left. Oh, left pp, left plus plus. All right. How do we find the next node on the left? So we're here. So we need to go up, right? We need to go up and then go down right. So parent shall be L stack dot pop and return down right. No. So we go up, and if it has a right, then we go to the right and then down left. So we say parent. If parent on right, return down right, down left, parent on right. Hold on, it doesn't make sense. No, it should be just that one. Oh, let me think again. And then I'm done, right? I'm done. It should be my parent. If I have right, then I need to go down the left. And when it's done, and I don't have a right, then I'll pop, right? A node. If I have a right, I go to a right. Yeah, no, it's not right. should be if .right, then return down left .right. And if there's no more left, then I will return this. Yeah, if I have a right, I'll down left from this. Otherwise, if I don't have a right, then we'll just return, not return myself because I'm already done, right? Because I want to go left PP, which means I need to return and then a pop. I think else stack.pop. Because on this side, when I'm done with myself, and I don't have a right node, so the ones larger than me must be my parent. So I will return my parent. Def right, yeah, left next to left, and this will be next to right. Okay, next right. So we finished this, we need to find something smaller. So if I have a left, so if no dot, hold on, that's different. Because I traverse on the most right, okay, it's the biggest value. And then go up is slightly smaller, and go this, and then we go all the way down. I want to find something smaller. So everything is bigger than this, right? So I go to the left, right? So if node.left, down left, which all the way, this is the current one, just smaller than me, right? Otherwise, then we can return rstack.pop. Otherwise means on this side, if I don't have a left node, so it should be the rstack. Okay, so we say low and high equals down left, root, down right, root and root. So while low is not high, if low.val plus what if it's empty? Can it be empty? No, it cannot be empty. If low.val plus high.val is equal to k, alright, we'll return true. Actually, I want to return true at the end. If it's smaller than k, then we say next left low, because low is going to become something bigger. Elif low.val plus high.val is larger than k, it's too big. Then next right high, else return true, and then we'll return false. Let's try this one. 4 solutions. Ooh, that is interesting. Empty list. Something is not right. What do you mean? There's no left? Alright, I have to check this. Let's see how this one work. 2, 7. Oh, this one works. Oh yeah, of course it works. 2, 7 doesn't work. Oh, low equals high equals. There you go. Yeah, that looked right. Try this. Ugh. All right, let's see what happened. Okay, this is our thing that we fail. What do we have? I have 0, -1, -3, 2, and 4. Okay. Expected true. Yep. -1 plus minus. There we go. Go all the way down, so it should be -3, -3, 4. Well, 1 is too big, so it should be -3, 2. -3, 0. Yes. It didn't keep going. Why? Why do you not keep going? Because I go back to the root and I stop. Next, right. So now we stop at the 0 at the root, right? And low is still not high, because low is pointing to this, high is pointing to this. It's -3, it's still larger than high equals right, next right. So next right for 0. So if 0, where? The left, yes.
Ow.
Then down left. Oh, then we go all the way down to -3. Oh, that's not right. Oh, it's not supposed to be down right, down left. What the hell? It should be down right. Alright, typo. Small typo. Small typo. Let's try it again. Alright, before we try it again, get all the test cases. Yep. Wow. Yeah, that is the solution. That's O log n. Yeah, it's O log n. I'll call it O log n. Why? Well, this is log n, right? And the traversal itself, yeah, the traversal takes some time. No, you know what? I don't think this is on. Because everything gets visited once. We do this, and then we move, and then yeah, that's on. These are on log n, but this is on. Angle from two side in, so this shall be the similar. Interesting. It is on. Yeah, it's the same. Maybe it's just slightly more than on. You know what? No, it is on because everything gets traversed once. Yeah, everything gets traversed once. Okay, good binary search. The week of binary search. All right, so we've done this. What's this one? Curious. That's fine. Iterator. The iterator idea. Let's see. Node list. Oh, I didn't even pass the node list. I call it push left. Same idea. And I just don't get a value. The other one I push the actual node inside. We call it OH space. Yeah, it is OH space. Okay, the calendar. So I have an idea with a calendar. So this is not maintainable, right? So what I have the idea is we sort based on start. If we sort based on start, right, then each one will have different extensions. Some will extend like this one, extend 20. Actually, just to check, because I have this idea while I was sleeping, so it might not be 100% accurate. We can try to 10, go to 20, 50, go to 60, 10, go to 40, 5, go to 15, 5, go to 10, and 25, where's 25? 25, go to 55, alright? So we sort based on starting position. So what we have, and we get the longest. Actually, it doesn't really matter, right? Yeah, it doesn't really matter the longest or not. So we say, doesn't matter, we just sort. 5, let's go just 5, 10, 5, 10, 5, 5, 10, 5, 15, 10, 20, 10, 40, 25, 55, 50, and 60, right? So the ideal is every time, because we sort of start, so new start, new period to come in, and we have if it's the same start as the previously, then the maximum number of occurrences for the previous start will be the same as the current start because they start at the same time, right? So we just plus 1. So 510 we have 1. 515 because 5 and 5. So this one will become the previous one plus 1. So this will become 2. Now 10 comes in, right? 10 is larger than 5. So what we need to know is on the previously, the maximum reach of the previous. So how many of the previous things that the maximum reach, the end, is larger than 10. So we can sort them, right? We and sort them 10, 15, binary search with 10, and this give me 1 because 10 and 10 doesn't work, so 10 has to go with 15. So 1020 is 1, all right? And then 1040, all right? 1040. Now the previous is 10, 15, and 20. And then 10 comes in. Now I have 2, so 1040 has 2. Right? And then we put 40 in. Next one's 25. If 25 comes in, we'll look at the previous ending. 25 comes in. Oh, then I have only 1. Now 50 comes in. This idea is not right. 50 comes in, that's only 1. Man, no, this is not right. How? I thought it's fireproof in my sleep. I thought it's fireproof in my sleep. Come on, man. So where are the 3s? The 10. 1, 2, 3. Oh, we cannot do it that way. Because we saw 5 first. Is when 1040 comes in. Or 1020 comes in. Oh, I see. So it doesn't really count. I have to count the previous one as well. Hold on, let me do this again. So previous one ending at 10, ending at 15. Right? Now 10 comes in. And when 10 comes in, I take 1020, right? 1020 comes in. That's 1, that's 2. 1020 comes in. That shall be 2. Why? Because I forgot to count myself, right? So 5, 10 is 1, 5, 15, 5, 5, so that's 2. 10 comes in, and then we binary search. So from the previous, I get 1, but 1020 itself, so that's actually 2. 1040, because it's the same as the previous one, so I just plus 1, so it'll be 3. Here's the 3. And then 2555 comes in. 2555. So 25 comes in. Previous only have 1, so that should be 2. Right? It is 2, because I want a maximum. So this one will only have 2. And 5060 is also 2. Okay, let's double check. 5 times 1. Yeah, this is like this one we have 2. And 10, like this point we have 1, 2, 3. Right? And 50 is 1. Actually, it's not 1, because like this period has 2. And 25, this period has 2 as well. Okay, so would it happen that, trying to figure out a situation, would it happen we have overlap on the actual things, but the start doesn't count? Yep, how about this? Let's say 110. Yeah. 110, 210, 310, 410. Using my idea, 110 will be 1, 210, that will be 2, 310 will be 3, 410 will be 4. Damn, it does work. because I sorted it. That's why it works. So I sort. It's always going from small to large. If I sort it, we always from start. Right? We sort the start. Right? So for each start, is the first time it happens, and all the previous one, I cannot participate. So for me to participate, right, it has to be, so each interval, if I have something, if I have some corridor, right, if there's some corridor, they gotta be a smallest that across everything. Alright? Yeah, if we have a corridor where everybody fits in, they gotta be one. That's the smallest among them that the other one has to include. I think this is valid. So let's try this. Okay. Oh, no, that's not the one I want. And I hate this. How do I get back?
Really good.
Oh, yeah. That's not new. I don't want new. Yes. All right. So what my idea is, we are going to get self.starts. Oh, I don't have everything, right? Oh, shoot. Wait, hold on. I think this still works. Wait, hold on. I just realized. Yeah, this is hold on. 1020. 50, 60. This is all one. That's fine. 1040. So 1040 will be here. Right? 1040 will be here. I just need a right. 40. So 10 comes in. You know what? This actually doesn't work. Like every time I have to sort. Maybe it's fine. We just sort every time. We only have 400, right? We only have 400 calls. So when it comes in, I just sort it, right? After I sort it, I binary search it. But then, and I return the maximum. Okay, so I add a new one. I binary search it. I add it, sorted it, right? I sorted this. Oh, I don't sort this. Oh, let me think again. Do I sort it? No, I don't sort. I just keep the right. Right. This is all we need is the right. The right is 20. Right? It's larger than. And the next one's 50. It's bigger, so I just put 60 here. Next one's 10.
Is the rent he's paying?
And then and then 10. Oh, but previous extending.
Wow.
50 has to be the ones that's
Oh, here there are.
started before 10. So I just go through everything and bring them out, and then yeah.
Yeah, Fanchen already offered to assemble it for me.
Grab everything, sorted it. Let's try it. Right? Just data.
First. Oh,
This.
We started a celebration with
Then what?
taking Jamba to the vet.
Self.k 0. Not K. Yeah, self.k.
Yeah, she has tapeworm,
0.
so
And that's it.
gave her
Book
medicine.
comes in, and we just say
No, because I think she had it before.
Mm,
and we've been.
temp
It's only
equals
through the fleet
for
that they can
left
get it.
below high in self.data. Right?
So,
We say
we've
if
been putting fleet
low is
allocation
smaller or
in
equal to
the
start,
Jamba since we got
and
them
then
all
we're gonna
between
sort
from
this.
before we adopted her. So
Then
I don't think Jimbo has.
we can.
No, it's only you can only get it if you eat the flea that's infested with
Do I add the current
The-
data?
tapeworm larvae. You can't pass it just by eating the tapeworm
Yes, I can.
segment.
I think. Let's do this. We're gonna append it. Start end. Sorted it. And
No, it has to be from a flea.
rest so equal
I
to
know there's fleas in the poop.
bisect right temp
Well, they're not eating each other's
and
poop. So.
start.
Yeah, that's
S and
how we
E.
saw it on Jamba. That's why we took her to the vet.
E.
We saw it.
Right?
Tapeworm segment. So.
And then
But we can tell if Jimbo will get it. But
if it's the end and if it's the same, I want to go to the first one. So I think I need a bisect
to art museum.
a left.
Yeah.
Right? A bisect left.
And then we went because Fanchen, the mom and dad of his cousin,
So
leaving soon next week back to
come
China.
this thing.
So
Or if it's in between, it's gonna come in this thing.
Wanted Fanchen to bring her
Index.
mail her snacks. So instead,
Let me say if
the cousin asked us if they wanted us to bring anything back to China. So okay, we bring the snacks.
then we
it
say
mailing. So we're gonna go just to drop off
if
the snacks when
temp
they just invited us in the house to chit chat, and we mentioned there was my birthday.
if these two are different.
Well,
right?
later the
If these
brought me the ring.
so in here, if these two are different value, then that's actually the solution. This is the number. Right? Then if these two are the same, then it will be the same position, right? Yeah, it will be the same position. It will always be this position. Because the one in front of it is just this position. So I do think index is the result. Right? I'm going to just say if self.k is smaller than index, self.k equals index, and self.k. Something like this.
It was really good. I've never had such a big burrito before.
Give it a shot.
It was like stuffed, like super wide burrito. It was like super heavy. I couldn't finish it all, even though I was hungry.
This should be a start.
Oh yeah, it has vegan cheese and vegan meat. Yeah.
What the heck? Come on.
No, todo, but they have the vegan option.
That's not right.
Then they have something called what? No, I think they make it themselves. They have something called pupusa. I never heard of that before.
Okay, 10:20.
No, de Mexico.
Okay, and then we say if it's a smaller than, we get an E out, so we got 20 out. Right, and then we're gonna bisect temp start, so index will be 0. Index is 0. And yeah, that's not right. It's a 0. Index is 0.
Yeah, so we also tried that. It was good.
Oh, it should be the remaining, right?
Yeah, really good. Also with vegan meat and cheese.
Yeah, it's not smaller than me. It's whoever is bigger than me. Whoever is bigger than me. Ah, I made a mistake here. I think it should be bisect right. So I want to know whoever is bigger than me. Right? I know the total number that's smaller or equal to me.
Not the restaurant.
Maybe I should still do it right. Right, so a common here.
From Google, I brought
that's the total number. Right?
And
vegan
ice cream.
This shall be len self len temp minus this is the total number that's larger than me. Then I can do this. Let's try it. This is a start. Almost. The 3 didn't get picked up. Hold on, let me see. 10:20 is good. 50:60, right? So 50, 60. And then I pick everything that's smaller or equal to 50, which is 60, that's 1, okay? So next is 10:40. And then it's I have 20 and 40, and I have 10. Binary search is 0. So that's 2. 2 minus 0 is 2. So we go.
Anyone else see my mask screen weird?
This is okay. Oh, what? I want to. Oh yeah, this is good.
No,
it's small. Yeah, that's good. Okay, so 2040 is good. 1040 is good. 5:15. Okay, hold on. 10:20, 50:60, 10:40, 5:15. Right? Now I get all the S that is smaller equal to start, but nothing is smaller equal to start. As a start is 5. Everything is larger. So this one, temp is empty. As index, no, temp is not empty. Temp is only 15. Right? It's 15. So that gets 1. So we don't get updated. Okay, so I think we are right. 1, 1, 2, 3. Oh, 5:15 is wrong. Oh, I see. 10:20, 10:40, 5:15. No, I think you have to search. Man, this will take time. So we'll search it. So we insert it, sort it, and to go one by one. Oh, I'm not sure. One by one. O and login, and then ON. Yeah, this is not right. Sort. Alright, and then once I sort, you have to go through everything. I don't have to. I think all I need is, oh, if I add a new thing. So I have to go from the large to small. Alright, because I add the start and end. So I sort the previous one. And now I add this into it. And then once I add this into it, I sort it again, then things will change. But the one that's smaller than me won't change. Then what we can say is for S in S and, but we want to get the end out, right? We want to get the end out and sort them. Hold on, let me think again. So if I get all the ends, sort them, and we go from this, and everything will hold on, let me think again. We have to start, right? And
stem cells.
I need to go from the new start, right? And for all the new starts, I need the previous. And I'm gonna go through everything up into this. So I sort the entire thing, okay? I sort the entire end. Oh, no, this is not gonna work. For each one,
Sometimes the cousin was saying, because they have their baby's now 9 months old, and they were saying how much work it is. No, they were saying like how much work it is to care for the baby.
Sort the entire thing.
Like, you have to be watching it. They can't go outside to
the entire thing, and we have to go from the yeah, we just have to redo the whole thing every single time.
And mess with different things, and if there's a stranger, he will start crying.
You know what? Yeah, I don't quite like this idea now. Yeah, I have to sort it, and then go from the smallest, and then I have to keep sorting all the ends. Right? Keep sorting all the ends. But do I need to keep sorting all the ends? Everything is larger than this, right? It's larger than 5. But then I need to know who is larger than 10. Then I need to know who is larger than 10.
I remember I was absolutely terrified of fireworks.
I'll try. Add, sort, then we need to find the one, because it's only the ones before will not change. Right? The ones before will not change. It's only the newly added. So I just need to handle the newly added. So we can say the first index can be data.
Sometime next week, I don't remember.
12. 12.
Oh no, I was just gonna say that Sunshine has an interview with Google on Wednesday.
Data and start. So that's the index.
Well, he already knows all the tips.
Right, that's the index. So when you go from this index down. So what we're gonna do is so the right.
I was too late. Apparently if the recruiter reaches out to him first, I don't get the money even if I refer him. If I refer him before a recruiter reaches out to him, then I get the money. And the recruiter already reached out to him.
Right? I to this index.
I didn't know that until after
self.data.
About to refer him.
Okay, this is the rights. Now we need to do is, because if it's the largest, then there's nothing, right? So we say for j in range, index to len, self.data. Alright, j in this range from index to the end. Now for every single one, I'll need to check the end.
He just needs to study behavioral questions now because
my start.
One of the interviews is behavioral.
Right, start. So what I need to know. Oh, hold on. No, I think this.
No.
This start.
Something extra. Like he doesn't have to prepare anything for killing.
I'll go left. I'll go left. So I get everything. Oh no. It was right. And I'll get everything that's with the star that's smaller or equal to me. Alright? And then among them, I will this is the rights. So this is the new rights. Right? Oh, hold on. Like these are the ones that's smaller than me that I need, like just for the current, for the current start, right? It's from the current start. Hold on, let me think again.
Yes, and please don't no significant others or other family members.
Hold on, let me think again. So, if I have...
I don't want this one to be a big deal. I want the celebration during Mexico.
If I have this thing, I have the start, I have an end, I have a start and an end, right? So I sort them based on starts, and I have both of the ends. And the new one comes in the middle, right? The new one comes, and then
I prefer it just
if anything changes, because I just need the largest value.
Unless you really want to, I prefer not to. Why? Because I just don't want this one to be a big deal. I don't want you guys in it. It's just because you guys want to.
Yeah, I have to rethink this. I'll see you guys later. Adios.